So in the My Uni notes, I've given you some key points for bending moment diagrams. Tips and tricks makes it sound like I'm a magician. It's not really. So it's bending moment diagrams, key points. And so you can have a look through those. It's best to understand where these are coming from rather than just trying to learn them. So try and understand why all of these things work. And probably the best way to do that, I know it's painful, but is to work through a few using the method of sections. So doing a heap of points with method of sections and see what it does. And once you've done that a few times, you'll understand where all these different tricks and rules are coming from. And bear in mind that if you ever can't remember in an exam, you can't remember the rules that you can use for a shortcut, you can just use the method of sections to plot a few points, and that'll help you figure out where the bending moment diagram should be. But it's awful quick if you don't have to do that. So rather than just go through all those points individually, what I'll do is just run through them graphically. And so first of all, we're saying, remember that internal force of bending causes curvature in the beam. So if you had a beam like this, curved like that, and then you had another one that was curved like this, it's not very well drawn, the bending moment for this one, certainly at this point, the bending moment for this is higher, and both of those would be a positive bending moment. They're sagging. If they were going the other way, it's called hogging. I don't know why it's called hogging. Then that would be a positive, that would be a negative moment. Okay, so hogging is negative, sagging is positive. And because of that, what you always do when you're drawing a bending moment diagram is you draw positive downwards. You just show that by drawing your little arrow downwards. And the reason for that is it'll end up that when you draw your bending moment diagram, it will look a little bit like the beam does. That's why we do that, so positive downwards. Then we have, I'm just looking at my list of rules and stuff here. So the first thing you're always going to have to do when you're doing a bending moment diagram is it's always best to find, well, it's not best, you have to find the reactions first. So you're going to find those reactions, and then you're probably best to draw your shear force diagram. You can actually go straight from this to the bending moment diagram, but not with the stuff I'm telling you. So you're going to have to draw your shear force diagram first. So go and draw your shear force diagram, and we've done that already for these two problems. And so quick recap, sorry for keeping going over the same things, but for a shear force diagram, all you do, if it's point loads, it's super easy. You just go from left to right, wherever you see a force, whatever the direction of that force is, you go the same magnitude in the same direction for your shear force diagram. And so this change in shear force is the same as the magnitude of that force. Okay, so we're going to go up, we're going to come down by the magnitude of F1 because it's pointing downwards, F2, and so on. And for the shear force, if it's a line load, it's very like going from shear force diagram to bending moment diagram that we just talked about. The easiest way probably to think about it is just think, look, to go from one point to another point, the change in the shear force will be equal to the area under the line load. And so in this case, if we go 1 meter, we've got 1 meter here, it's W1 here, the area under is got W1 times 1 meter, so it's just W1. So for every meter we go along, we have to go down W1, along, down W1, along, down W1. Okay, and because we'll only work with rectangular loading, we're not going to go to the point of triangular loading in this course. And so you'll end up with a straight line. Anywhere between forces, it's a horizontal line, and so on. Now, so that's how we get the shear force diagrams. Can't remember, go back and look at that summary. That's that. And so for bending moment diagrams, another thing to remember is if at the end of the beam you've got a pinned connection, which might be, well, if you're, let's just draw them as they're really just little symbols to pretend to be something. So a pinned connection like that, or you might have a roller, or you might have, let me just draw the end again, you might have some kind of rocker on the end. Anything like that, then you're going to have zero moment at that point. Built in is different. And so if you've got a cantilever, haven't really done one of those. We'll come back and talk about the cantilever. What I'm going to do is highlight it so I don't forget about it, but it's not going to be zero at this end. because that support has a moment reaction. These supports only have X and Y reactions. So first rule is, if you've got a moment diagram, if you've got a pin or a roller, the moment must be 0 at that point, as long as it's at the end of the beam. So what I've done here is I've just drawn on the axes for my moment diagram. So as usual, I'm drawing positive moment down the way. And then what I'm also going to do, just to make it a bit easier to explain, we would have these values if we were doing this with numbers. And so I'm just going to call them, that's V1, V2, V3, and V4. It'll just make life a bit easier as we go along if we know those. Excuse me. I'll get to this next one in a minute. Okay, so this problem here was this one. It's all point loads. And we figured out our reactions. And then we've drawn our shear force diagram. And now we're going to go from that shear force diagram to the bending moment diagram. Excuse me. The nice thing about that is the way to do that is exactly the same as the way you went from a line load to the shear force diagram. So line load to shear force diagram, exactly the same thing when we go from shear force diagram to bending moment diagram. It should just, and so let's get started. And so as we already mentioned, let's go back and look at this one again. It's got pin connections at each end. This represents a pin connection. We have X and Y reactions. This one represents a roller. It would just have a Y reaction. But we know for those pin connections and rollers that the moment at that point is going to be 0. And so we know that's going to be 0, that's going to be 0. And now we draw the bending moment diagram. Oh, and just another thing, the symbol for moment, bending moment is M, just the same as moment. The symbol for shear is B. And so those rules, we just do exactly the same thing. For every unit we go along, the moment is going to change by V1 kilonewton meters. So again, it's just the area under this up to the point you're at. So I would do V1 times 1 meter. And so that would be V1 kilonewton meters. And so in this case, if we were counting squares, this might be, so this is 3 squares up, so it might be 30 kilonewtons or whatever. If it was 30 kilonewtons, we'd be going down 30 kilonewton meters. So positive directions down. This is a positive shear. So it's going to give us a positive moment, which is going to be down the way. And for each meter we go along, oops, sorry, that's not right. So for each meter we go along, we're going to go down V1 kilonewton meters. Just the area under the curve. This one goes for 2 meters. Like so. Okay, and I'll just put this on to remind us. So what we're saying is, if you go along 1 meter, along 1 meter like that, then you're going to go down V1 kilonewton meters. And it's just the area under that UDL. And same as last time, you could go all the way to the end and get the total area, and that would be the total amount you'd have to go down the way. So that's 1 meter. And this would be V1 in kilonewton meters. So you've times it by the length, the base. So it would be V1, but it would be in kilonewton meters. So it would be like a moment. Same as this one. No, we'll not say that. Okay. Then we do the same for the next bit. Still positive, so you're still going in the positive moment direction, which is downwards. But this time for every meter you go along, V2 is much smaller, just a tiny fraction of a square there. So you'd be going down V2. You just have to kind of estimate this a little bit. Be like that. Am I on fat here? No. Just make that fat. I'll come back and tidy these up later. So again, if I was to come along 1 meter, 1 meter, I'd come down to get rid of that, I'd come down V2 kilonewton meters. The change in moment is just equal to the area under the shear force diagram in the same way as that the change in shear was equal to the area under a line load. So now we've got V3, so this time it's negative, so we need to go in the negative direction for a moment, which is upwards. And so for each square we go along, we're going to have to go up V3, which is about 3/4 of a square, whatever its value is. So it might be something like that. Yeah, something like that. I might have to fix this a little bit later. Come all the way to the end of that part of the shear force diagram. I'm just looking at where I am. I'm just a little bit high because I know I've got to get back to 0 because this is a pin. Obviously this is easier if you're using numbers. You can just figure out the numbers. So let's come up. Just think about that. Yep, it's about there. So for that part of the shear force diagram, for every meter you go along, you're going to go in the negative direction by V3 kilonewton meters. So 1 meter along, V3 kilonewton meters. The last one, just the same thing again. It's a horizontal shear force diagram, and so for every meter we go along, we're going to go in the negative direction because it's a negative shear force by negative V4. And that's going to bring us right back to 0. And so we know we're on the right track. Let me just draw it on. If I can get a meter, the whole thing is a meter this time. Come along a meter. You're going to go in the negative direction because it's a negative shear force. And this is going to be V4 kilonewton meters for every 1 meter. Okay, too easy. Now, there's only one other thing to say about that, and that's another of the key points, is that if you've got 0 shear, you'll end up getting a maximum for your moment. Now, it's just a local maximum. So what's going to happen, wherever there's 0 shear, the moment's going to go from going positive, positives downwards, it's going positive to going negative. That's what happens when you cross a shear. So you get these kind of local maximums or minimum. It could be going negative and it changes to positive. Excuse me. Let's just look at that for some of the other ones we've done already. So for this one here, here's our shear force diagram. So that was this loading. The shear force is 0 here, and that's the point at which it goes from the moment is getting larger, going positive, to going negative. Find another one. So you can see at each of these points where the shear crosses the 0 axis. So we've got 0 here, 0 here, 0 here. In this case, it's going positive to, it's going in the positive direction, then it's going in the negative direction. Here, it's going negative to positive directions. So negative direction changes to positive direction. You've got 0 shear. This one is going positive and it keeps going positive. So there's no 0 shear there. But here we've got it's going in the positive direction, changes to going in the negative direction. You've got 0 shear. So you've got these little local maximums and minimums wherever the shear is 0. Again, that'll be true for any diagram at all, that'll be true. And so that's quite useful sometimes for finding your maximum moments and minimum moments as you look for the zeros on the shears. And it's a good way of checking your results as well. Okay, that's pretty much all I've got to say for the first one. As always, hatchet a bit more neatly than I would do. What I'll do is I'll just tidy this one up a bit, and then we'll have a look at this other example. Okay, so let's do a real quick recap of where we're at. And so we've had a look at if you go to a force, so if you've got point loads, and you're figuring out the shear force diagram, you just follow the forces. So if you've got a force upwards, so the shear force diagram starts at 0, and then you just move upwards by, if you've got a force upwards, you move upwards by the same magnitude, and then you go horizontal between forces. This force is downwards, so I go downwards by the same magnitude, 0 between forces, and so on along the beam. So it's really easy to get from a point, so a beam that's got point loads in it, to the shear force diagram. Of course, the first thing you did was figure out what these reactions were. But after that, dead simple to find the shear force diagram. That one was easy. Then we went along to have a look at getting the shear force diagram from a line, if you've got a line load. So remember, a line load is just where you spread the load out evenly over a certain distance. And so it would be in terms of kilonewtons per meter or newtons per millimeter or something like that. So we've got a line load here, and we looked at how you get the shear force diagram from that. And this time, the main rule to remember is that the change in shear force between any 2 points is just equal to the area under the line load between the same 2 points. So everything I'm getting is just coming from that rule. And so what you can do is, first you figure out the reactions as usual, and you might change it into a point load to get those reactions, but just when you come back to internal forces, you need to change it back into the UDLs, otherwise you get the wrong answers. And so you might find an equivalent point load for these two to find these two reactions. Well, you not might, you would. And then what you'll do is you'll just change it back when you start working with internal forces, because those equivalent point loads don't work for internal forces. Then the rule to find the shear force diagram. So you could take that rule. So the change in shear between any 2 points is just equal to the area under the line load, and you're allowing for the direction of that line load. And so, for example, in this one here, so what we could do is we could take the area just in 1 meter sections. And so we'd have the area, so to get to this first meter here, let me just draw it on, we would take this area here. And so that would just be W1 times 1, which would be W1. And so it would just go down W1. And that's always the same as you move along. So for this next little section to go another meter, we'd have to go down another W1, because the area under here is just W1 times 1. And that way you can go down this stepwise. And when you draw those points, you'll see it's a straight line. So it's always the case that shear is a straight line under a rectangular line load. And we're not going to do triangular line loads in this course. But there's another option. Let me just see if I can get rid of that. So if you remember that this is a line load, you can just jump to the end of this. You can find the area under the whole thing. So you don't have to find the area under each meter. You can find the area under the whole thing. That wasn't very well drawn. Let me just zoom in a fraction. So we could find this whole area here. So that would be W1 times length 1, and we could do that jump all in one go. And then we'd remember, well, it's a rectangular line load, so it's going to be a straight line. And we've got to get the amount you'd have to jump is the area, which is just W1 times L1. And so you'd jump down that distance, or that shear. Okay, and we're going downwards because this line load is going downwards in the shear. And shear's not so confusing because positive is upwards. Okay, and then between forces, same rules apply. There's no load. Then we'd get to a force, we'd have to jump by that amount downwards, following the force. Then we're just doing the same rules for this next line load, and so it's going downwards, so we're still going downwards. And for each meter along, it's now half times W2. Sorry, it's just for each line load, it's W2. W2 is a half a square, so it might be, if this was 10 kilonewtons per meter, this might be 5 kilonewtons per meter. But so what we're saying there is you could either do 1 meter, for every 1 meter long, you'd have to go W2 down. That's what this here is showing. Just do that in the right thickness of line. Or you could jump the whole thing in one go and just remember that it's a straight line. And so you could go in steps. For every 1 meter, you're going down W2, where W2 is the magnitude of the line load. Or you could just do the whole thing in one step, and then you just find the total area under here is what you'll have to move to get to the end of it. And so therefore you'd be doing W2 times L2 to do the whole thing. That's the area. And then the last little bit, there's no load again, so you're horizontal again. Then we get to a reaction. Oh, sorry, I know it's a bit, makes you seasick when I do that. And so then you're just going to jump back up by that R2. I haven't really put that. So let me just put that delta. So delta V is equal to R2, and here delta V will be equal to R2. Now the nice thing is you just follow exactly the same rules when you're changing a shear force diagram into a bending moment diagram. So the rule is to change, so to go from a shear force diagram to the bending moment diagram, you're just finding the area under the shear force diagram. And if it's a positive shear, that's going to have a positive change in the moment. But you just have to remember that positive is downwards on the bending moment diagram. And that's to make it look a bit more like the deformed shape of the beam. And you can do the same thing. So you can do it stepwise. So you can think, how much would it change for every meter you go along? Well, it's just the area for every meter that you go along, and that would just be V1 times 1, which would be V1. So for each meter along, it changes by V1, and I should probably put delta M for each meter. But you don't have to do it that way. You could also do the whole thing in a oneer. So it's still the main rule is the change in the shear force is equal to the change in the moment is equal to the area under the shear force diagram. Just trying to think how I can draw this on so you can actually see it. And so we could jump the whole thing in one go, like so. Go like so. So if this was L1, then let me just rub out a little space. Oh, not so good. Just rub out a little space for me to write this in. So this here is L1, then the change in moment would be equal to L1 times V1, just the area under. Just going to make a bit more space for myself there, equal to L1 times V1 or V1 times L1. So the change is just the area under that. And so you don't have, so you can go in steps and just think about the change for each meter, or you can go it all in a oneer. And once you've remembered how to do this, you know how to do this, as long as you remember that positive moment is downwards. And some other things for moments, if you've got pin connections at the end, or a roller or a rocker, the moment's going to be 0 at that point, so that gives you a starting point. And we'll do an example that's for a cantilever in a minute. I don't have a cantilever in these ones. Okay, but the trouble is, so it's always the case, usually the case, that finding the moment from the shear force diagram is very similar to finding the shear force diagram from a line load. And there's even a similarity for force to shear force diagram, and that's if you're going from a pure moment to a bending moment diagram. We'll get to an example of that as well as we go through. We've kind of done one already, but we'll do some more examples just so that this sinks in. But what we don't have is we haven't looked at how to go from a triangular line load to a shear force diagram. And so, but the rule is the same. So let's do that next for this bending moment diagram. I have actually changed this a little bit. And so I've moved this force across. That was just so that the squares work out nicer. It's a bit easier to see what's going on. What I've also done is I've just labeled some different shear values on this. So these would be numbers in a real example, but I'm just using a general case, so I'm just putting letters on those. Our starting point is the same. If you've got a pin at the end, both of these are pin connections, so that's pinned and that's a roller with a pin. Then what we can do is we know some starting points, so we know we're going to be starting from 0. Wouldn't be the case if this was a cantilever. And it's going to finish at 0, this moment diagram. And if we don't get back to 0, we know we've done something wrong. Then the next thing we do is we realize, so it's still the case that the change in moment is going to be equal to the area under the shear force diagram. That's always true. What we have to be careful about this time is that the area under that shear force diagram is changing. So the amount it changes each meter is also changing. And so this is not going to be a straight line this time. As we already talked about, it's going to be a quadratic. It's going to be a curve. And so let me just highlight that. So we could do this here, and we'll call that A1. And then at this end, that's going to be A2. And what does that mean? Well, it means that if I just do a quick sketch, moment positive downwards, this is a positive moment, a positive shear, so it's going to lead to the moment increasing, positive shear. Negative shear is going to lead to the moment decreasing, and positive is downwards. So what's going to happen with this one, at the start there, let's go along so we've actually got the right number of squares. For the first square, it's going to change quite a lot. See, like so. For the next, so for 1 meter along, say, if this is 1 meter, it's going to change quite a lot because A1, this area is quite big. But by the time we get to the end here, it's hardly going to change at all. So it might be something like that. And so what we're going to end up with is some kind of curve like this, because the amount it's changing for each unit of length we go along is reducing because the area is reducing. Again, that's why you're getting a curve. So for this one here, let's make a start. And so we know that for over that first meter, or whatever that is, the magnitude of the shear force is going to change, the magnitude of the moment is going to change by the area under the shear force diagram. And so it is just going to be, let me just draw it all, just do some points. I'm just counting squares to get that. But that change there in the first meter is the best place to draw this. So say that was 1 meter. Then we might come, we'll just come this way. It's a little hard to see, that's okay. So for that, and I should have done those light. See if I can make them thin. I can. And there. The change in moment is just going to be A1. And A1, in this case, so there's a couple of ways you can figure this out. You could just divide it into a rectangle and a triangle. So you could do V2 times 1 plus V1 times 1 times a half, because that's a triangle. Or the other way you can do it is you can just take the average of these two. So you get a rectangle. You're doing a rectangle like that, really. So you take the average of V1 and V2, so V1 plus V2 divided by 2, and that'll also give you the area under that little section. But however you do it, you're just figuring out the area using the actual values of shear force. So if this was 5, let me just see, if this was 4 kilonewtons, this was 3 kilonewtons, then you just do 4 plus 3 divided by 2, which is 3.5 times 1. See what I mean? Oh, went too far. And so that's going to be equal to, because it's 1 meter wide, it's just going to be V1 plus V2 divided by 2. And that's just got our first point. And then we've got a bit of a choice about what we do next. I'm going to just change the numbers here just to make this a bit easier. So we could do A2 as just the next meter. So we could go stepwise. And so we could just use A2 as the next meter. And this time, we're going to do V2 plus V3 divided by 2. Get the average of those two and then times it by 1 to get the area. We can just count squares here because we're doing it all to scale. So it's 2.5. So it's going to be 2.5. So that's a half, 1, 2. So it's going to be here, the next point. And then we'll just keep going stepwise. Next one's 1.5. If it was numbers, you'd just be doing V3 plus V4 divided by 2 times 1. But there is another option. Rather than doing that, you could go straight from 0 to 2 meters. And so then you'd be figuring out the area. I'm just tracing it out with a cursor. The area under the whole thing, which would be 1, 2, 3, 4, 5, 5. These two together, 6. And you can see that's what it has changed for going 2 meters. 1, 2, 3, 4, 5, 6. See what I mean? And so then you would have done V1 plus V3 divided by 2 times L1. So the length, or maybe it's called L2, but that would be the length here, L2. So you don't have to go stepwise. You can go straight from one point to the next. Just be careful. Whatever you're doing, if you're thinking about the change between 2 points a certain distance along, it's the area under the curve for that distance. So where were we up to? Drawn this in the wrong place, I reckon. Should have been here. Just tracing it back up. And then we've got one more meter to go along. This would be V4 plus V3. V3 is just 0. That's because I changed things around to make it 0. It wouldn't have to be 0. And so in our case, we just go in half for the last one. So it looks like that. Now I will keep doing it actually. I was just going to say. Okay, so far so good. Then we've got nothing happening. And so the area under here is not changing. And so the change in moment is equal to area under the shear force diagram. If there's no area, then nothing will change. So it's just going to go straight along to here. Now the area has gone negative, and so we're going to have to go in the negative moment direction, which is upwards on a moment diagram. And we've got a force here. So there is a force here. It doesn't matter though. It doesn't really make any difference that the force is there. The shear force the change in moment is just the area under the shear force diagram. And so what we'd have to do here, we'll go along stepwise again, because for these ones with the triangular shear force diagram, so you've got an inclined line, it's best to go stepwise because then you see the curve. So you see the curve coming out and it helps you draw that curve. If you were to try and jump straight to here, you might join it with a straight line, and that would be wrong because the area is changing, so the rate of change of moment is also changing between those 2 points. Anyway, let's call this, I've got it already, V5, and that's V6. That's cool. Probably need one in the middle though, if we're going to go stepwise. You might have to figure out what that V6 is. If it's a straight line, it's halfway along. It's going to be halfway between V5 and V7. And so if this was 2 kilonewtons, this was 3 kilonewtons, that would be 2.5 kilonewtons. Anyway, what we can see is, to go from this point to this point, the area under this would just be V5 plus V6 divided by 2, times the length is 1, so it would be just V5 plus V6 divided by 2. In our case, we're counting squares. It's 2.5 squares, so it's going to come to here now. Again, for the next step, we just look at 1 meter. V6 plus V7 divided by 2 would get our answer. And so in our case, just saying that's 1.5, but is it really? It's not really. So I'm thinking to myself here, so say this was 2 kilonewtons, and this would be 2.5 kilonewtons. So that would be, if you find the average of that, it would be 2.25. And so in fact it would be here, 2.5, something like that. And here, does that sound right? Yeah, this is 2.5 kilonewtons, say. This is 3 kilonewtons, say. So that would go 2.75 would be the area under here. So you'd find the average of those times it by the length. The length is 1, so it would be 2.75. So that's 0.75, 1, 2, so it would bring it to here. And then the last bit's a bit easier now. This time it's a horizontal line. So this bit is should be a curve. It is. It's not much of a curve, but it's a curve. That's why it's good to go stepwise, just so you can see it. This last bit's horizontal. And so it's just like these ones. It's going to be a straight line, because as you go along here, you could divide this also up into tiny little sections. You don't have to use 1 meter, as long as you multiply by the distance you've gone along and get the area. And you can see that each of these areas is staying the same because it's constant. So the change in moment is also the same for the equal distances. That's why it ends up being a straight line. And so we end up with a straight line here, and it's going 3. It's the area under the whole thing is 3. So we're going 3, and it's a straight line, which will bring us back to 0. And so we know we've got it right. Then we just freehand draw the best curve we can through the points. I have to admit, you're always looking at the point you're trying to go to when you're trying to draw a nice curve. I'm not particularly good at it, I have to admit. Then we're going to come along horizontal here. Now this was another curve, which is extremely hard to do on a screen. It's a bit easier on a piece of paper because you can turn the piece of paper around. But we are going to get some kind of curve through here. Go like so. Okay, and there we've got our bending moment diagram. So I'll just put on the little mnemonics to remember that. We're pretty much done. And so that's everything you need to know. We're not going to go to triangular, starting with triangular loads, but the same rules, you could use exactly the same rules. It just gets harder to find these points in the middle to try and figure out what's going on. By that point, you kind of need some knowledge of integration and differentiation, which some of you won't have. And so we're not going to go on to triangular loads. Okay. So what we'll do now is we'll just do some numerical examples, just using all those different rules. I know I do an awful lot of examples, but it takes a bit of getting your head around this stuff. So I want to do heaps of examples. But when you're working through those in the My Uni, try these ones first, then look at the answer. Don't just scroll through them. You won't learn this by reading it. You'll only learn it by doing it. And that's true for this whole course. You learn by doing when you're doing this sort of kind of mathematical stuff. You don't learn anything just by listening to me talking. You try it, then you look at what I've done, and then you go, all right, that's what I got wrong, or oh, I'm fantastic, I got it all right to start with. Good. Stop.